All right, let's do some more bonus problems. Start with 308 in the textbook. So that says, use implicit differentiation to find dy dx for 308 is xy squared. Sorry, xy squared plus 3x equals y squared. Now there's two ways of doing this. You could use the chain rule a lot, or you could just simplify this first. I would highly recommend simplifying it first. For monomials, you can just square each one, and that's because, right, xy squared, it's just xy times xy. There's no foiling or anything because there's no addition. You can just rearrange the terms. Multiplication is commutative. It can be written in any order. It's one of the reasons to see why this is the case. But if there's addition and stuff, you really have to watch out. Let's take the derivative of the left-hand side. And let's take the derivative of the right-hand side. And again, we're taking the derivative with respect to x because we're looking for dy dx. All right, we're going to have to use the product rule on this first term. Derivative of the first thing times the original second plus the first thing times the derivative of the second. Don't forget your dy dx because of the chain rule, implicit differentiation. The derivative of 3x is just 3. Derivative of the right-hand side is 2y dy dx. And to be very clear about what's going on, this is that from the product rule. This is that. And this is that. Now we need to get all the dy dx's on one side and everything else on the other. And that's going to be a little bit messier here. Okay, so let's do this in 2 steps. First, let's subtract 2xy squared and a minus 3 from both sides. And that'll give us, let's rewrite this term right here. 2x squared y dy dx. And then we eventually need to move this term over as well, but we don't have to do it yet. Now let's subtract it over, and we'll get 2x squared y times dy dx minus 2y times dy dx. Now let's factor out a negative 2xy squared plus 3. Factor and solve for dy dx, and we'll be good to go. So, oops. You get dy dx times 2x squared times y minus 2y. We could factor that even a little bit more. Equals negative 2xy squared plus 3. Divide both sides by what's in parentheses. And you're going to get negative 2xy squared plus 3 over 2x squared y minus 2y. And that's a good answer. There's a couple things that you could do with this answer to make it look a little bit better. Like specifically, you could distribute that negative into the denominator and factor a 2 out of the denominator. If you put the negative in the denominator, it switches the order and makes one negative and the other not. And we can also factor out a 2, and that would leave us with y minus... Oh, we could factor out a 2y rather, sorry. And that would leave us with 1 minus just x squared. Oh, and then you could keep factoring if you wanted. 2x squared y plus 3 over 2y times 1 minus x times 1 plus x. We usually like things factored in the denominator, but you don't have to. That boxed answer is perfectly good as well. All right. You could check your answer by plugging in a point and finding the equation of a tangent line. We have a little time. Let's do it. Let's check our answer on this one. So we're going to plot the original relation, which was something. Xy squared plus 3x equals y squared. What is some? So this is what it looks like. We could plot some point that we see. Let's plot the point 1/2, 1.414. Wait, isn't that just the square root of 2? Yeah, I think it's actually probably exactly the square root of 2. Well, the tangent line is going to be y minus the y coordinate equals the slope, which is the derivative at this point. The slope is negative 2xy squared 2x times y squared plus 3 divided by 2x squared times y and y is the square root of 2 minus 2y. So the slope is about 2.3570 times x minus the x coordinate. And hopefully that's the tangent line at this pink point. Could zoom in a little bit on the x coordinate. And you can see that, yeah, we got a tangent line right here. This doesn't prove that our answer is correct, but it, because right, our answer is for all points. This is only checking it for one point, but it does tell us that at this specific point, our answer is correct. Just a good way to, doesn't prove you're right, but it can very frequently prove that you're wrong. 318. Find all points of this graph that have a vertical tangent line. The y cubed minus 27y equals x squared minus 90. Now we want vertical tangent line. Well, vertical tangent line means the slope is undefined. Slope or derivative is undefined. And graphically, we should be able to kind of look and get something. Right? Y cubed minus 27y equals x cubed minus 90. And who knows what this looks like. Oh. Wait, really? Oh, I didn't write negative. Negative 20 and 20. Oh. Huh. So we should expect 4 answers. Visually, we should expect 4 answers. Vertical tangent line here, 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 and here. Well, let's use calculus to get the answer. We're going to take the derivative of both sides with respect to x. And get 3y squared dy dx from the chain rule. Minus 27 times dy dx. We're taking d dx of both sides. We're taking the derivative with respect to x of both sides. Factor it out, dy dx. 3y squared minus 27 equals 2x. Or our slope is 2 times the x coordinate divided by, let's factor that denominator. We can factor out a 3. We can factor it even more. Difference of squares. And what are we doing? We want a vertical tangent line. We want the slope of that tangent line to basically be infinite. We want to know when is the derivative undefined. Well, a rational function is undefined when the denominator is equal to 0. This is going to be undefined when the denominator equals 0. So that's when y is plus or minus 3. And you might say, but Jason, there were 4 points. We have to figure out what are the x coordinates. So let's look at this function and find when y is plus or minus 3, what is x? So when y equals 3, what is x? When y equals negative 3, what is x? That's going to give us 27 minus 81 equals x squared minus 90. This is a quadratic equation. It's a simple quadratic equation, but it is a quadratic equation. It's going to be negative 54 plus 90 equals x squared. Or x squared is 36. X is plus or minus 6. So a vertical tangent line at positive 6, positive 3, negative 6, positive 3. And we do the same thing over here. We're going to get negative 27 plus an 81 over here equals x squared minus 90. That's now a positive 54 plus 90 equals x squared, or x is equal to, x squared equals now 144, or x is equal to plus or minus 12. So it can be positive 12 and negative 3, and negative 12 and negative 3. These should be the 4 points where we have the equation of a vertical, where the relation has a vertical tangent line. And you can see it. Yep, those are the 4 points that we found earlier. Here, let me get it all to fit. Vertical tangent lines. And again, this is not a function, right? This fails the vertical line test very definitely. This is a graph of a relation between x and y. And these are more difficult to work with than functions because you can't just plug one thing in and immediately get another, right? When we know y is 3, it took a little bit of work to find out what x was. Functions are nice. We're not dealing with them here, though. All right. Let's do 327. Consider a closed rectangular box with square base, side x, and height y. Closed rectangular box with square base and height y. So the base is x by x, the height is y, like so. What am I doing? 327. So we're going to need an equation. We're going to need 326 first. So let's do both. Find an equation for the surface area. Well, the surface area, it's going to take a little time, right? It's going to be the bottom plus the top plus all the sides, right? So bottom plus top plus 4 sides. And all the sides are going to be the same because it's a rectangular or a square base. The bottom and the top are both going to be x squared. And each side is just going to be x times y. So this is the surface area of this rectangular box. Right, bottom and top. 4 sides, like so. That's 326. If the surface area of the box is 78 square feet, so we're saying the surface area of the box is 78 square feet. Find dy dx when x is 3 and y is 5. Well, if this surface area is 78, that surface area is 78. 78 equals 2x squared plus 4xy. In other words, this relation has all of the boxes with a surface area of 78 square feet with a square base. There's infinitely many boxes with this amount of surface area. And we want to know what's the rate of change of y with respect to x at this specific box. So specifically, 3, 5 should be on this graph. Okay. And it is. So at 3 comma 5, the rate of change of y with respect to x, dy dx, at this specific size box, if we increase x by a little bit, how does y change to still be one of these boxes? Well, if it has 78 square feet surface area, then if we increase x, y should have to decrease as a result. Dy dx, this is just as x increases by 1, how must y change? It's a slope. So we should expect a negative answer. So we need the derivative with respect to x. We take the derivative with respect to x of both sides, and we're going to get 4x plus, we're going to have to use the product rule. That's our first guy. That's our second guy. Derivative of the first thing times the original second plus the first thing times the derivative of the second. We need to solve for our slope. So let's have 4x dy dx by itself and subtract over everything else. Divide both sides by 4x. We're going to get negative, let's factor out a negative 4 and have an x plus y. And then a 4x over here. And the 4's cancel. That's our slope. And specifically, we want to know about the slope when our base is 3 foot by 3 foot. And our height is 5 feet. So we just plug that in. All right, so the derivative with respect to y, whoa. When x is 3 and y is 5, it's just what happens when you plug in 3 and 5. It's going to be negative 3 plus 5 divided by 3. Or what is that? That's negative 8/3. At this specific size box, what's the rate of change of increasing x? So if we increase x by a foot, y should decrease by about 2 1/3 feet. Okay. What are our units here? That's a good question. So the units for a rate are always what are the units of the top divided by the units of the bottom. Meters per second is the rate of change of position over time. Well, the rate of change of y is feet, and the rate of change of x is also feet. So the units are in feet per feet, and you could write that and that'd be okay. But this is what's known as a dimensionless quantity. All right, there actually are no units here. Oh, I just slapped my thing. All right, and that's what it's going for here. And again, as a reminder, you'd always check your answer to these odd problems. Sometimes the book has errors, but if you have something else, think there's an error, just ask me about it. Let me know. We're looking at 327. Says negative 2.67. Is that what we got? Yep, that's negative 2 2/3. Negative 2.67. Great, we did it. Let's do one more problem. I don't know if I want to do this whole problem, but I do want to talk about it. 328. Use implicit differentiation to determine y prime. Does the answer agree with formulas we've already determined? X is a sine of y. So y is not a function of x here. X is a sine of y. So y would be the inverse of sine of x if the inverse sine existed. But let's look at the distinction. This is what we're talking about. This is not a function. All right, this is why when we talked about trig and we talked about finding inverse sine, which by the way, let me show you what inverse sine is. Inverse sine is just that little orange piece. It has to do with domain restrictions. We restricted the domain of sine so that it was 1-to-1, so that it passed the horizontal line test, which made inverse sine pass the vertical line test. That's why we had to do it. So we're asking in this question, what is the derivative of this relation? It's not a function. Okay. Well, we use implicit differentiation. Take the derivative of both sides. The derivative of the left-hand side with respect to x is 1. The derivative of the right-hand side is the cosine of y times dy dx. Okay. Okay, we're fine. I lost it for a second. And I'll show you why I lost it for a second. Let's solve for dy dx by dividing by cosine. We get 1 over cosine of y, or the secant of y. And my first thought was, well, that's not good, Jason. Derivative of inverse sine isn't secant. It's 1 over the square root of x squared minus 1 or 1 minus x squared. I always get them flipped. 1 over square root of something. So what's the deal? It's because this is y, right? This is the rate of change of y with respect to x. And we have 1 over the cosine of y, but what is y? Well, we don't really know. Y could be found by taking the arcsine of both sides. What do they really want you to do here? We know, all right, so we know what the sine of y is. That's what they want you to do here. We know what the sine of y is. We know the sine of y is x. So what's the cosine of y? So that's similar to what we did before when we introduced this formula. So the sine of y is x over 1, and you can draw a little reference triangle here. Okay. And then in the past, when we drawed our reference triangle, we said, all right, there's only really one situation that can happen. But here there's infinitely many situations. And that's where that plus or minus is going to come into play that we didn't have to worry about before. So again, reference triangle. If y is some angle, the sine of y is opposite over hypotenuse. Y is some angle in radians. So to find the cosine of that y, we need to know what goes here. And before, we knew that to be positive, but here we don't know whether it's positive or not. It's either going to be positive or negative. We're going to have to choose. So you do some work and you're going to get the square root of this squared plus this squared equals that squared. So you're going to get the square root of 1 minus x squared as that x coordinate. So the cosine of y is just adjacent over hypotenuse. And again, here it really is plus or minus. We don't know the sign in generality. We only knew the sign of that, or I'm saying sign. I'm saying this sign. We don't know the positivity. Whereas before, when we looked at the derivative of inverse trig functions, we made some assumptions that told us that, yeah, we only have to worry about the positive side. Because cosine is only positive in this area. But now we're looking at every area, so it is plus or minus. So 1 over that cosine is the reciprocal of that, which is plus or minus 1 over the square root of 1 minus x squared. So this is very, very close. Very, very close to what we had before. Before we had no plus or minus for the derivative of inverse sine. Right? Where the sine is decided by, specifically it has to do with y, and the actual reason for which y it is really, really hard to, well, it's not really hard. It'd just be messy and not worth our time right now. I think I've already done enough rants in this section about things that are a little outside the scope of this class. So again, this is actually what your official answer would be with the techniques of this class. But this is how we connect it to what we've talked about before. All right. That's kind of a fun little thing. But that's pretty much it. Let me know if you have questions, and bye-bye.